Hello everyone. In this demo session, I will show some example from Kmeans neighbor classification, and also I need to show some example from Kmeans clustering. And I think these examples are so useful for assignment 5, and let's go on the example, and we start with Kmeans neighbor classification on iris dataset. So at the first, we need to, as usual, we need to import NumPy and mass module in the in the Python, and then random module. And also we need to import Kmeans neighbor classifier actually in scikit-learn. So let's run this, and then after that we need to load the iris dataset to create training and validation and test sets from this dataset. So this means that at the first, actually the training set is used to train the Kmeans neighbor classifiers, and we need to evaluate the classifier on test set, which has no overlap with training data. And also we have another set, which is the validation, and then validation set is actually another set which has no overlap with training and test set to the peak value from for hyperparameters, for example K. And as you know, in Kmeans neighbor classifier, we have a hyperparameter K, which is actually the number of neighbors that we want to count in our algorithm. So in this cell, what I'm doing is actually dividing the data that we have in iris dataset to training set, test set, and the actually validation set. So by this line, actually we are getting the data dot shape 0, which is the number of points that we have in the data, and then try to sort this number of points randomly, which can give us a list from indices for data that we have in iris dataset, and try to sort them in random order. This is because we want to select randomly from data points for each test, train, and validation set. And then I get 70% of data for training, 15% for validation, and then 50% for tests, right? So massfloor return largest value to these numbers. And this can show that the number of training point that we need to have in training set. Same here for number of validation point and validation data point, and we find the indices of these numbers to use in the training and then validation and then test set. So by doing this, we are splitting our data in Iris data set to train set, validation set, and test set. So let's run this, and then, for example, here we print the number of training that we need in the output, the number of validation, and also I show one example of data point in the test set here. And you can see these are features, and the last column is the label for this data point. And these also can be so useful for the assignment 5 because for the training set, we get all rows and all column except the last one as a training input or features that we have for each data point. And we get the last column as a label for each data point, right? So by this line, we are separating the features and the labels for each data point in the training set. And then again, we are doing that with validation set and then test set, right? So in this case, we have training input, training labels, validation inputs, validation labels, and test inputs and test labels. And if you want to know that the shape of each features or labels, you can just call a variable features from each NumPy array, which is the shape, and return the shape of each array. For example, for the training inputs, we have 105 number of points that we mentioned here. And for each one, we have 4 features. These are features. And for the labels, we have just one one-dimensional array because for each data point, we have just one label. So we just return 105 labels for each data point in the training. Same here, we have 22 data points for validation that we mentioned here. And then for each one, we have 4 features and 22 label for each. Actually, we have 1 label for each data point in the validation. And if you want to see one training input or features, you can just print the indices that you want. For example, here we print the 3 data points from training inputs, and then the corresponding label for each data point. And let's run this. And then finally, we have data, and now we can use a k-nearest neighbor classifier from scikit-learn that we import here. And as you can know that these function can get an input, which is the number of neighbors that we want to count in each new data point. which is we assigned it the value of 5 here, and then we call it name, and then this module has a function which is the fit, and then the fit function get the train inputs, which are the features of the inputs, features of the training data, and then we get the labels for each data point. And this can just actually fit is a kind of training function, and then these are the features, and then assigning these features to labels. And now this nate that we just created with K-nearest classifier has another function which is predict, and this function gets actually the validation inputs for 5 data points that we have in the validation data set, and predict the labels for each one of them. So, and we have also another function which is predict prob, and actually this is the probability of actually it's a probability of each class that we have for each data point. For example, if we have 3 classes, for each data point, this function return a probability that means the probability that this data point is from this class or not. So let's run this, and then I need to run this before that. So at the first, I show the features from, for example, 5 data points from the validation data set, validation set. And also I show, I print the labels of these 5 points. And then use the predict function to predict the class of each data point. And you can see the output here, which is exactly same as the labels that we have, which means that the k-nearest neighbors can find the best solution for the best labels for validation input for these 5 data points. And if we want to know that the probability of assigning each data point to each class, we need to use this function, which get the features of these 5 data point, and then return for each data point, return array of the 3 numbers that are, for example, this one means that the first data point, this one, cannot be from the first class, and the probability of assigning this value to class, the third class, is 1. And as you can see, the predicted label for the first data point is 2, which means that this one is 0, 1, and 2, and then we return 2. And for the second one, for example, the probability of assigning the second data point to class 1 is 0.8, and so that the label that they assign to the second point so second data point is 1 because the second class has a high probability compared to other classes. And so if we want it, this also can be a useful function for finding the probability of each class for each data point. So if you want to see, for example, one data point and the feature of this data point from the validation set, you can use the index of 1 to the feature that we have in a NumPy array. And so by doing this, actually we are fitting the training data in a k-nearest k-nearest neighbors classifier, and try to predict the labels for validation set data point. And you can do that with also the test, and I show some example from the test in the next cells, but there's another function that I just mentioned here, which is the actually k-neighbors, and this function get an argument, which is the valid input, and these function return the k, actual k is equal to 5 here, and then this function return the k closest neighbor to each data point, and also return the indices of this data point. So let's run this cell, and at the first we print the distance to neighbors for each data point that we have in the input, right? So this means that the first data point that we have in the validation set, the distance between this data point and the one of 5 closest neighbors of this data point is this, and you can see the distance to all 5 closest neighbors for each data point here. And this also is the indices of closest neighbors for each data point. Right? So yeah, you can use the indices of the closest neighbors to find the feature of each neighbors by doing this, because this return the indices of the neighbors, and if we want to know the feature of this data point, we just need to pass this index to training inputs, and we can get the labels of that neighbors by passing this index to the trained labels, right? So until now we saw that how we can use k-nearest neighbors and fitting data to this classifier, and then get the label for the validation data point. Now we want to know that how we can evaluate the k-nearest neighbor model on the test set. So there is another function for actually for this classifier, which we created here with this constructor. and the name of the function is a score, and these function get two arguments. The first one is the test input, and the second one is the test labels. Actually these function apply the test input and get the labels of these inputs from K-nearest neighbor model, and then compare each label to the test labels that we have for each data point, and then return a score between 0 and 1. So this means that if the K-nearest neighbor model can find the actually can predict perfectly all the labels of all the data point that we have in the test input, this score function return 1. And so let's run this, and the score that we get is 1, which means that 100% the predict of the labels was true. And if you want to see the prediction of each test input by K-nearest neighbor model, you can call the function predict and actually pass a test inputs to this function. And then we print that, and then we also print the test labels that we have, true labels for each data point that we have in the test set. And you can see both of them are exactly the same, which means that the K-nearest neighbor model achieved the best performance on the test labels or test set. And you can also compare these two lists by this operation which we saw before. We have double assign sign, and then this can return a true false for each indices for each index in these two lists. For example, the first one is equal to this, that the first index in these two lists are same, and so the output is true. As you can see, for all of them are true, which means that we are getting 100% accuracy in this dataset. So this also an example to show how we can evaluate the model on the test set, and we have just one remaining question, which is that how we can select the best K value, because we just assign the value of the K in the constructor by 5, but how we can say that, how we can set this value. And we can do that by running some actually training on the training inputs, and then get a score of the K-nearest neighbor model on validation inputs, and find the best value for the best score for each K, and select the best one on the validation. So note that we cannot do that with the test set, but we can use the validation set, because the other model shouldn't see the test set in the training phases or using actually the selecting values for the hyperparameter. We just need to use the validation inputs. So let's run this cell. And as you can see, we start from 1 up to 15, and the step size is 2, which means that we get the k start from 1, 3, 5, 7, 9, 11, and 13. And then for each one, we make a classifier, make constructor for the k-nearest neighbor classifier, and then fit the training input on this classifier. And then after training and fitting the data on this model, we get the score for the validation input and then validation labels. And this is the accuracy of the classifier, and then we print it. And as you can see, the best values for the k are 7 or 9. So we just need to set the value of the k in the classifier by 7 or 9, because these are getting the highest score compared to other values. And if we want to putting the whole codes together to run a classifier on the training data, we just need to fit a model with the best k and see how it does on some test data. So we just need to run this, and then we assign this k to equal to 7, and then fit the data on the training input, and then get the score of the model on test input and test labels, and get the test accuracy, which is the 1, which means that we are getting 100% accuracy on the test. So these are the examples that I have for the k-nearest neighbor classification, which I think is related to the lecture 9. And also I have another Jupyter notebook for the lecture in the Kmeans cluster that we actually have in the lecture 10. And also we have just one simple example problem in the assignment 5 for the Kmeans cluster. You don't have to implement the Kmeans cluster from scratch. You just need to use the scikit-learn models. But I want to show some example from these clustering to show how it works. And so at the first, we import the NumPy and Matplot, and I also import a counter module from the collection that I will describe why we need this. And I also import cdist from SciPy, which can compute the distance between two data points that we need to use this in the Kmeans, and also I think in the k-nearest neighbors classifier. So because we are using this function in the assignment 5, and I'm showing an example of this function here. So let's run this, and we also know that why we are inputting, why we are assigning initial value for the numpy random, because we want to get the same result each time that we run our cell to make sure that everything is fine. So doesn't matter that. So at the first we make some data point or cluster to show a two example of the K-means cluster. So for the first cluster, we get the 20 random number from a normal distribution, which has 2 dimensions each data point, and then the standard deviation of that is 0.05, and then the mean of the data points is 2. And we get another cluster by generating 100 points, and then for each one we have also 2 dimensions, and then the standard deviation of these numbers is 0.5, which is much higher than this one. And then the points are, the mean of the points are between, actually the center of these points are 1 and 5, which is a 2 dimension for each data point. So this means that we are making data point near these points that we have in the 2 dimension. We get another, actually we get another cluster with 50 points, 2 dimension, and these are near these points in 2 dimension. So I actually I actually stack this list vertically to make the data set that we need for the K-means clustering, right? So I'll also use the scatter function to show this example. So let's run this cell, and actually the S argument here is the size of each data point that we have in the plot, and we just pass this let's see this array, and then I will show which is related to each cluster. So for example, this one just return the old rows that we have in the numpy array for the first column. If we want to know the data that we have for the second column, we just need to pass the second index equal to 1, and you can see that. And if you want to know the shape of this array, you can just call dot shape. and I just need to print that. So we have the 20 numbers from the first cluster, 100 points from the second cluster, and 15 from third cluster. So these are the numbers that we have for all data point, and each data point has 2 dimension. Actually, each data point is has 2 index. No, it has 2 features, which can return a 2-dimensional array for us. And for the scatter plot, we just need to pass the first dimension and the second dimension for all the rows. And as you can see in the output, this one is, I assume this one is the first cluster because the standard deviation of them is so small. And as you can see, all of them are together. And the mean of them is near the data point 2. So we have all of them in this point. So for the second cluster, we have 100 numbers by 0.5 standard deviation, and all of them are should near this data point. So which means that we have all of them here because we subtract that, and -1 and -5, we have lots of numbers from the second cluster. And for this one, we should have all of them here, most of them here near this data point, because we add this data point to each data that we have we generate by random number. And we didn't change the standard deviation, so a standard deviation is 1 as a default number. And for the first step of the Kmeans clustering, we need to generate some random number as a cluster standard. And so we just need to select generate 3 data points because k is equal to 3. So we generate 3 data points with 2 dimensions, and the standard deviation is 1.5. So these are the cluster centers, and then for each one we have a specific color to show in the scatter plot, and then we pass in the scatter plot we just plot the points that we have in 3 cluster, and also we plot each data center that we have by a marker or the color of the cluster. And we also pass s is equal to 125 because we want to have the cluster centers larger than other points. Now, so let's run this, and you can see the data center that we just randomly selected are appear in here, right? So in the next step of this algorithm, we need to assign each data point to each data center. So we define a function which get the points and the center and find the distance of each data point to each data center, and then for each data point we find the closest data center by calling np.argmin, and then we pass access to 1, which means that we need to find the smallest number in each column for each row. So this means that for each data point, we find the closest center. And I just want to mention that these functions get 2 arguments. The first one is the array of the points, and the second one is the array of the centers. So, for example, if you have 2 data points and two center cluster center, so we get the cds return array of 2 by 2, which is kind of like this. And so the first element is the distance of the data point 1 and cluster center 1. So another one data we in the second column in the first row we have the distance between data point 1 and the second cluster. The same we have in the second row data point 2, second cluster center of 1, and then we have the second data point and the second cluster. So this can return in actually a 2-dimensional array to specify the distance between points and center of clusters. And so let's run this cell to see the cluster of each data point. So I just need to run this cell to define the function, and then I will explain this function, but before that, I just want to show the plot that we are getting from assigning the centers to each data point. So for example, for this data point, the closest center is the red one, right? So we are assigning this data point to the red cluster. And for example, for this data point, the distance between the distance between center clusters are computed by this module, cdist, and then we assign the blue one to this data point. So this is the second step of the algorithm, and then if we want to update the center, and which means that we want to find so in the third step we need to update the center by actually the points that we are assigning to each cluster. For example, here we assign these data points to the red cluster. So in the third step, we need to find the center of these points, and then update the center for this cluster. So I just need to run some example, and then I will come back to explain these two functions. And for the assigning center, I just run this, and then you can see that. And then I want to update the center for each cluster. So I expect that the center of this cluster would be near something like here, because for example, for this point, the center should be near this position. And let's run that and see. So as you can see, the center changed, the position of the center changed here. And actually it relocated to this point, and then this is the second cluster and the center of that, and then we have the updated center for the third cluster. So actually the updated center get the point, and the assignment and the center return the new center for each cluster by getting the mean of points that we assign to each cluster. And this also is a show plot that we are calling for each cell that get the points and the assignment on the center, and just try to actually plot the points by the color of each class, each cluster. And that's it. And we are not going to do the until the conversion, because we need to do this step to convert to a solution for the clustering. But I just want to show some step of this algorithm. And there's some notes on assignment 5 that I want to mention, that I think that would be useful for doing the assignment. So for the first note, I want to show an example of cdist function that getting two arguments. The first one is the two-dimensional array that actually the two-dimensional array, the rows are points and the columns are features that we have for each data point, right? And also we pass another two-dimensional array, and then the cdist to return the distance between each data point from the first array and the second array. So for example, let's run this, and then for example, this is the distance between the first data point from the first matrix, and the distance between this data point and the first data point from the second argument. This is the distance between the first data point and then the second data point in the second argument. So as you can see, the distance between them is 1, which means because the first features for each for these two data points, actually the distance between them is 1, and the second features are equal. The second features is equal. And this can also be useful for finding the closest centers or closest neighbors in the k-nearest neighbor classification, and finding the centers in the closest center in Kmeans cluster. And also, I want to mention another function that we have in the assignment 5, which is the select most common label, which is the useful function for finding the most common labels from neighbors of each data point. So this function just get a list of numbers, which each number is a label for example, all nearest neighbors for each data point. And we create a counter that get the list and return a dictionary that maps each value to the number of times it appears. For example, here, if we pass this list to this function, so the output should be 3, I guess, because we have 3 times of this number in the list, and this is the most common labels that we have in the list, right? So the output is 3 because the counter return, let's print the output of this. Maybe it's easier to describe. So as you can see, each value to the numbers is assigned to each key. For example, here we have 2 yes, we have the number of 2 is appeared here 3 times, right? So 2 is a key, and then the value of the 2 is 3. For 3 also, the value is 3, and for 1, the value is 2, and then 0 is appear just once. And then we find for each items that we have in the dictionary, we get the labels, which is the number of times that each number is repeated in the list, and then the numbers that we have. And then we sort them to find the most common labels from this list. And that's it. I think I show some example from lecture 9 and lecture 10. And if you have any question about the assignment or the content of the lecture, as usual, you can ask me by posting it on Piazza or email. And that's the end of the session today for today. Bye now.